Hello students, welcome to this lecture. In this particular lecture, we'll quickly go about understanding the asynchronous part of the set and clear signals, especially for the latch and the flip-flop designs. And asynchronous in the sense that whenever we press the set and clear, irrespective of the clock level being high or irrespective of during the edge transition, wherever we press the set and clear signal, we should get the output to be 0 or 1 as we press the clear or the set signals. Right, hope that with that particular understanding, let's move ahead. Let me also pick my pointer. Right, so this is what we had seen in the last lecture where it was a synchronous set and clear signal for the flip-flop. So it is, that's what the synchronous represents, that only when the phi is equal to 1, the level high. And if we press the set or clear signal, we will get the output to be 1 or 0. So what it really means is that, during the clock level to be high, we have to maintain the set and clear signal at least before the T setup, and it should be retained after the clock edge and then till the T hold time. So it should be the clear signal or the set signal should be retained for this entire duration of the setup and the hold time with respect to the negative edge of the clock, because this is a negative edge triggered flip-flop. Right, so that is when I will get the proper output. Right, so let's have a look at the asynchronous part, and let's try to understand with the latch design first. Let's take only the clear control signal for the latch design. So this is something we had already seen, except this particular portion. So this, just to summarize this, if I apply the clear, if I press the clear here, I will get an output of 1. This output will be passed through the transmission gate during the high level of the clock, and then the output will be 0. So, whenever I press the clear signal during the clock level to be high, I'll get the output to be 0. Right, and then this is, this is the clear, and then the D signal path are provided to the 2-input NAND gate. So here is a statement saying that the NAND gate is clearing the output during whenever the transmission gate is passing the signal. So that is when the clock is high, right? But because I want an asynchronous portion, so that means that even when the clock is low, right, and if I press the clear signal, I need the output to be 0. So to accommodate that, there is a tri-state 2-input NAND gate, right? It is called as a 2-input NAND gate, but there is a clocked NAND gate, or rather I'll call it as a, the clocked NAND gate or the clocked tri-state NAND gate. And this is there to clear the signal, clear the output during the clock level being low. So during the opaque mode of the latch, right? So now let's have a look at this. So the 2-input NAND gate, it is nothing but, at the transistor level, it will be nothing but the NAND gate. So if I consider, these two transistors in the pull up side, and then, these two transistors in the pull down side, and then these two transistors in the pull up side. So that becomes like a 2-input NAND gate. But because it's a tri-state or a clocked NAND gate, so we will have two transistors here, one on the pull-up side and then one on the pull-down side. And that those are provided, or those are fed by the clock signals. So this behaves like, this completes the clocked NAND gate schematic. Right, so what really happens is when the clock is low, here, both these transistors will be on for the NMOS transistors, and then the clock being low, so the clock bar will be high and clock will be low, so this PMOS will also be on. So both these transistors are on here. So the output here, which is provided to this particular X node, right? So this particular X node here depends on, what is the Q signal or what is the clear signal. So in this particular case, because it's a 2-input NAND gate, whenever the clear is pressed, right, I will get the clear bar to be 0. So I will get the X to be 1 here, and then this will throw the output to be 0. Right. So this particular output being comes to 0 through when the clock is low, comes to this particular tri-state or the clocked NAND gate, and when the clock is high, and if I press the clear, the output of 0 is passed through this particular 2-input NAND gate. So we have used 2-input NAND gates here. One is the regular 2-input NAND gate, the another one is a tri-state or a clocked 2-input NAND gates to get the cleared output, right? And this, both this NAND gates will pass the output or will make the output to be 0 during the different levels of the clock. So that's why we call it as an asynchronous clear signal, right? Remember that even when the clock is high here, let's say if I have a, this is the clock high, and if I make the clear, press it for some time and then depress it. So during this particular portion, so let me write this as clear, and then I will also have an output of Q. So during this particular portion, so the output, let's say it is high, and then during this particular portion it will go low, right? And it will stay low because the clear is pressed, and then when the clear depresses, then it may come back high depending on the D output signal or the D input signal, right? So it clears within this particular clock cycle and then comes back. If the D is 1, so then it will come back to the D input, right? So whereas in the clock bar signal, whenever it gets cleared here, the Q will be retained to 0, right? Because the D is not allowed in the clock whenever the clock is low, right? Because this particular transmission gate doesn't allow when the clock is low here. So the transmission gate will be off, so the D doesn't pass. So in the low level of the clock, if the clear is pressed, then the Q will be 0, it will be retained, right? Whereas in the high level, whenever it is the clear is pressed, and if it is depressed, it will get back the D value, right? So that is an added information here. Now let's have a look at the asynchronous clear signal for the flip-flop designs. And if we can understand this, then I think we can easily go or incorporate the preset or the set signals. And then finally, we will have a look into the latch design accommodating both clear and the preset signal. So asynchronous clear signal for the flip-flops. Now what it really means? It means that whenever the clock is high, if I press the clear signal, then I should get the output to be 0. And if the clock is low, if I press the clear signal, the output should be 0. All right. And the output should get the updated value of the D only during the next clock edge, right? And in this particular design, the first latch is the positive level of the latch, and then the second latch is this negative level of the latch. So this particular flip-flop output or the flip-flop design is considered to be a negative edge triggered flip-flop. So with this particular understanding, right, so what we really need is, if I press the clear signal during the high level or during the low level, I need to have the Q to be made to be 0, and Q should wait for the next clock edge, for the next negative edge or the falling edge of the clock, so as to get the updated D value. Right, so let's say that I've written 3 conditions here. So let's look at it one by one. So during the 5 bar, so that means during the clock being low, let's say that this is the design I have, and just a disclaimer here that it is an incorrect design. Right, so I've added the clocked 2-input NAND gate here. I have added the clocked 2-input NAND gate here. Because this clocked 2-input NAND gate here was, when we inserted that, then we got the clear signal, the asynchronous clear signal for the latch. And with that understanding, I have put both the clocked 2-input NAND gate in both the latch designs, so as to get the asynchronous clear signal for the flip-flop. Right, but again, I'm just reiterating again that it's an incorrect design. So let's see why it is an incorrect design. Right, so let's take the first case during the 5 bars. So during the 5 bar, and I have annotated this first NAND gate, second NAND gate, and then the third NAND gate. The second and third NAND gates are the clocked NAND gates or the tri-state based NAND gates. So during 5 bar, what we are saying is, if the clear is pressed, then the clock level is low, so the tri-state will pass this. Whenever the clear is pressed, I'll get the output to be 0 here. So this 0 will make the X, or rather, the output, whenever the clear is pressed, the clear bar will be 0. This output of the tri-state or the clocked 2-input NAND gate will be 1. So this X will be 0. So that's what it is mentioning here. And this X will be 0 because the clock level is low here. This is going to pass the 0 here, and then the output will be 0. Right? So this seems to work well. When the clock is low, and if I press the clear signal, the Q output turns out to be 0, which is good. Let's say during the high level of the clock, the first NAND gate, is going to pass, clear is pressed. So this will be 1 here, this will be 1 here, X will be 0 here, and X will be 0 here. But the phi bar, it's not going to pass, because the clock is high here. So I got an X value of 0, but the second transmission gate is not going to pass this X is equal to 0 to the other side, right? Because the clock is high. Right, so in that sense, the second transmission gate doesn't pass the output to, doesn't give the output to be 0. It has to wait till the next, the negative edge comes, right? Which is not what we are expecting. We expect the moment the clear is pressed, I'll get an output of 0. So the high level of the clock, this particular design doesn't achieve. Right, so let's say, what happens with this particular 2-input NAND gate. Right, so this 2-input NAND gate is, we wanted it to be giving the Q is equal to 0 when the phi is equal to 1, when the clock is high level. But this is not giving that. This is giving the right output when the phi is low. Let's talk about this third, the clocked NAND gate, or the third NAND gate. So third NAND gate, when the phi is high, so that means this phi is high, that means this, the 2-input or the tri-state or the clocked NAND gate will give me the right output. If the clear is pressed here, when the phi is high, so I will get an output of, so clear is pressed, so clear bar will be 0, so this will be 1. And the output here will be 1. Right, but this is incorrect because we want the Q to be 0. Right, so that's why we say that it's an incorrect design. Right, proceeding further, so what should be the right design? So let's try another another configuration, second configuration here. And in fact, if you look into this flip-flop designs, I've removed the NAND gates from here, I have removed the 2-input NAND gates from here, I have removed the 2-input NAND gates from here, and I've just pressed taken this 2-input NAND gates here. Right, so this particular NAND gate is not clocked at all. So if it is not clocked at all, the moment if I press the clear signal, I will get the Z to be 1 and Q to be 0. Right, so irrespective of the clock here and here, if I make this 2-input NAND gate very, very close to the output, and if it is not a clocked one, so irrespective of the clock and irrespective of the D input, if I press the clear signal, I'll get the output to be 0. Seems to be very, very satisfying, but there are some problems here as well. So let me go over that. Let me go over these two cases. So during the phi, during the high level of the clock, if the clear is pressed 1, then I'll get, based on the D signal, this X will be D, whatever is the D value, this X will achieve D, that's what I have written here. But the Z is 1 here, because clear is pressed, and then clear bar will be 0 and Z will be 1, and then the Q will be 0. So irrespective of the D signal, I'll get the Q to be 0. During the low level of the clock, if the clear is 1, right, Z will be 1 and QZ will be 0. Right? Again, during the low level of the clock, irrespective of all this transmission gate, tri-state inverter, tri-state clocked inverter, the output will be 0. Seems to be satisfying, but the problem here is it is actually momentarily 0. And why I am saying that it is momentarily 0 is the moment if I depress this clear signal, right, whatever was the X previous, right? So let's say that I have a clock here, and during the low level of the clock, right, low level of the clock, so this is when, that is what we are considering at this particular low level of the clock. So let's say I have an input from D, which is gone, and, this X will contain the D value based on the high level of the clock, right? Because this transmission gate will be on. So during the previous high level of the clock, right, I will have an X is equal to D here. All right. And this updated D value is waiting here, right? But because, and, when it goes to the, the clock goes to the low level, that is when during the falling edge or the negative edge of the transition, this X is going to be passed here because of this particular transmission gate is now on. But what really happens is, because the clear is pressed here, somewhere here, so I'm going to have the clear signal. So let's say that the clear signal is here. This is my clock, and then the clear is somewhere it is pressed here and it is depressed here, right? So because the clear is pressed here, I'll get an output of 0 during this particular portion of the clear signal. But then after that, once it goes down, this x is equal to d is there. This x is equal to d will be passed here. So the d signal will be passed here, right? Although I will have this, whenever this particular value is z is equal to 1 and q is equal to 0. So the moment clear is depressed here, it will take this particular signal, right? And then I will get the q to be nothing but d. So the moment the clear is depressed, q will become d, and which is not what we want. What we really want is, from the circuit design, what we need to, the way we need to accommodate the clear control signal and the set signal is, the moment we press the clear signal or the set signal, the Q should be 0 or 1, and it should stay to 0 or 1 till the next, the negative edge will come. So till the next negative edge means I'll have to wait for this particular edge. And it should not change anything during this level of the clock, right? Either during the positive level or during the negative level. It should change only in the next subsequent edge, falling edge in this particular case. So in that sense, this is a wrong design. So Q will get updated with the previous value of X the moment the clear is depressed, right? Again, which is not a good design. So the better design is what I have drawn here. So this is the third configuration design. So what we need to do is this particular portion, right, which was creating a problem, right, because the d was passed here. So this particular x value, if it had retained the d value during the positive level of the clock and it was waiting for this clear to be depressed, and the moment the clear signal is depressed, this x will be passed to the output, right? So whenever the clear is pressed, we need to ensure that this x signal is also cleared. And for doing that, now in this particular better design, there is a clocked NAND gate. So this clocked NAND gate will ensure that when during the phi bar here, the transmission gate, when it is likely to pass the x signal onto the other side, during the phi bar, this x signal should be cleared. Right, so if I press the, if I have this clear signal pressed, I know that the output here will be 1 and this will be 0. But at the same time, this will be 1 here and then x will be 0. Right, so no matter what is the d here given, right, during the phi bar, so this will be off. So this transmission gate will be off, and then x will take the value, or it will take the precedence of this particular tri-state 2-input NAND gate, which is driven by this clear logic. So x will be 0, and then this 0 will be passed or will be maintained even if the clear is depressed. This 0 is going here and then will be retained, so the Q will be 0. All right, hope this is clear. So what we have accommodated these two NAND gates. One, this particular NAND gate ensures that the clear output is 0 during the phi level of the clock, right? And then during the phi level of the clock, it is actually maintaining this particular path, because this tri-state inverter is our it maintains this 1 and then makes this 0. So this node is staticized, and this staticized node ensures that it doesn't this particular path dominates and then keeps this value to be 0, right, during the phi phase, during the clock level high. Whereas this particular clocked 2-input NAND gate will ensure that during the phi is low, during the clock bar or the phi being low, this clears the output, right? Hope this is clear. So let's try to accommodate the clear and set signal both for the flip-flop. And we already know that this particular NAND gate will ensure that during the phi is high, the output will be 0. And this particular clocked a NAND gate will ensure that when the clock is low, the the output will be clear. So how do we accommodate the set signal as well? So to accommodate the set signal, we have this particular portion and then we have this particular portion, right? And here, the bubbled OR gate is used. The bubbled OR gate is nothing but a NAND gate here. So, and this bubbled OR gate, one is the tri-state bubbled OR gate, which is nothing but the bubbled or rather the tri-state NAND gate. And here it is not a tri-state, it is just a forward passing bubbled OR gate. So it will be nothing but a 2-input NAND gate, right? One of the input is the set signal. So a set bar is given to the bubbled one. So what it really means, if the set is high, so I will get the output of this OR gate to be 1. Similarly here, if the set is high and if the clock is whatever is the clock that has been given, so if it is the clock is high here, so during the high level of the clock, I will get, if the set is 1, I'll get the output to be 1 here. Right. So the way this works is, if the set is 1 during the negative level of the clock, if the set is 1, so I will have the this output to be 1. So during the negative level of the clock, this transmission gate will pass the 1 here. And then this one particularly will give the 0 here, assuming that the clear is not at all pressed. So again, the condition is, if the set is pressed, the clear will be depressed. And if the clear is pressed, the set will be depressed. Right. So this 0 will be passed and then the output will be 1. Right. So during the negative level or the low level of the clock, this particular bubbled OR gate is going to maintain the Q is equal to 1. Right. And then during the high level of the clock, if this is set is 1, so I will get the value 1 here, and then this will be 1 here, and then 0, and then 1 here. So the clock, whenever the clock is high, this particular bubbled OR gate will ensure that the Q is 1, and when the clock is low level, this particular bubbled OR gate is ensuring the output to be 1. Right. And similarly, we have anyway seen the clear control signals that have been accommodated or incorporated by this two input NAND gates. So hope this is clear. So we have seen the asynchronous set and clear signal for the flip-flop. The last one is the asynchronous clear and set signal for the latch designs. For the latch designs, what we are seeing is an asynchronous clear signal, which was accommodated by this particular 2-input NAND gates and this particular 2-input tri-state or the clocked NAND gates. But if I want to accommodate the set signal, pretty simple. The synchronous clear and set signal, however, we have designed, we had this the 2-input OR gate, and then that is being followed by the 2-input NAND gate. For the synchronous clear and set signal, so the same designs will come here in the forward part, and in this particular, instead of an inverter here, so we have used the bubbled OR gate, right? And then in this particular OR gate, we will apply the set signal. So here it is the set bar and here it is the set. So this particular forward path will ensure that when the clock is high, if it is either set or clear signal that has been pressed, we will get the output to be, if it is either set, the output will be 1. If it is clear, the output will be 0. And when the clock is low, this particular, clocked 2-input NAND gate or this particular bubbled OR gate will ensure that the output is 0 or 1 during the phi being low. Right. So this clears, this completes the asynchronous control signals for the latch designs as well as the flip-flop designs. And in this particular lecture, we actually looked into the incorporating the asynchronous the control signals such as the clear and set signals for our latch and then the flip-flop designs.